Okay, so this is a video lecture for Math 1053 at UTSA. This is for the Module 1 content. Well, .on 1, I suppose. Module 1. For whatever reason, these PDFs aren't labeled by module, just like the topic is on the page, but not like module numbers anyway. So basically, the way these are going to work is every week I will record a lecture like this. I will basically work out all of the examples in this document. And the idea being that either on your own or from the video, you rework the problems, make sure you understand them, and then turn that in. It's an easy grade. So every week you need to turn in your lecture examples every week. Yeah, so I'll also sometimes sort of do like a sidebar and talk about concepts a little bit if I think it's important. Obviously, this is like a pre-recorded lecture, so it's not like I can wait for people to ask questions about stuff, right? I have to anticipate what those will be. So I won't spend a whole lot of time doing that just because, especially early on, maybe no one needs it, but there will be times where I say, okay, we need to talk about this concept a little bit. So all these things in this module 1, these are all prerequisite stuff. It's all stuff that you've probably seen at some point in the past, and some of it you might know well, and some you might not know so well. And also, there's a lot here, but we're just going to work through all of them. And I'm also going to try not to edit this video. I'm going to try to do it all in one take. It's just easier for me. That might be obvious, but also, just having it more like what it would be like in a class where if I make a little mistake, I have to fix it right then, right? So if I make a little mistake, I need to fix it in the video. So let's jump into it. So the first several ones are just about using like PEMDAS, order of operations, like doing this without a calculator, right? Obviously, you could type all this in a calculator and the calculator will give you an answer. But in order to do stuff later in the class and then also in the calculus class that comes after this class, you need to understand what's happening. Just typing in the calculator is not the same as you understanding what's happening, right? So we need to make sure that we get that. So I'm looking at this, and I guess I'll talk about PEMDAS a little bit up right here. So PEMDAS, which you've probably seen before, that is a not very well done capital letter D, so PEMDAS, right? So that stands for, as you probably know, parentheses, exponents, multiplication, division, addition, subtraction, right? It's an acronym that helps you remember stuff. So parentheses and exponents, you need to kind of think, okay, I need to look at the parentheses, I need to look at the exponents. Stuff that's inside parentheses has to be resolved before stuff that's outside parentheses. And there are some exceptions to this. And by exception, I don't mean that PEMDAS is wrong. It's just that PEMDAS is more restrictive than you actually need. Kind of like if you're making cookies with a recipe, right? If you follow the recipe exactly, you will get cookies and they'll be fine, right? But if you were to tweak the recipe just a little bit, you might get better cookies potentially. So it's kind of like that, where PEMDAS is like the recipe version. Just follow this, it always works. But you can go off script sometimes, and by getting better at algebra, you'll learn when it's okay to go off script a little bit. And so at times I will do that, and I'll try to remember to point out that I'm doing it. So in this one, the 2, the exponent of 2, and the 6, they can't do anything until after we resolve stuff inside the parentheses. So let's do that first. So looking inside the parentheses, I have a bunch of stuff, right? I have plus, I have an addition, I have a sum, and I have a product, right? Well, in PEMDAS, multiplication, let's do a different color here. Multiplication has to go before addition. So this one actually has to go first. Like I said, there are sometimes exceptions to that, but in this case, that's just the only way to do it. So I'm going to do 3 times 2 makes 6. So I'll have 5 plus 6 squared minus 6. Okay. And then I'm still working with what's in parentheses. So 5 plus 6 makes 11. And I can drop the parentheses. I don't need them anymore once that's all worked out. Okay. And then 11 squared is 121. Minus 6 is 115. And sometimes you might think, well, yeah, 11 squared is kind of hard because to do that in your head might be kind of difficult. So sometimes you're going to need a calculator anyway, especially when the numbers get larger. You're just going to need one. But we need to understand what is the process, what is the order of operations, so that when things get more complicated and there are variables involved, and a calculator can't just do it for us, at least not like a handheld calculator, we need to know what we're doing. And that's going to be very important so that later in the calculus class that you'll be taking next semester, that you understand algebra well enough to make it in the calculus class. And what I mean by that is, in calculus, about 80% of what you do is algebra. So if your algebra is solid, then calculus will be very manageable. If your algebra is not solid, well, then you're going to have to do more work to flesh out your algebra during the calculus class, and that makes it harder. So, when we're asking you to do things, it might seem a little silly, like, yeah, but why wouldn't I just use a calculator? Well, next semester, you won't be able to just do that. So you kind of need to develop the understanding as we go along. Anyway, I'll try to stay off the soapbox. So next, and feel free, obviously, to pause any of these and just try to work it out yourself and then skip ahead and see what the answer is. If you think you know how to do it, just go ahead and do it. So following PEMDAS, there are no parentheses, so exponents have to go first. So I need to work on the 5 squared. So this is 2 times 25 plus. Now this is a chance where you can go off script, because I'm going to later do the division before the addition anyway, right? Multiplication and division go before addition and subtraction. So later on, I'm going to get 3 from 6 divided by 2 before the plus does anything. So if I want, I can go off script and do 6 divided by 2 makes 3 now. I don't have to. I can. I'm going to not do that, although I could have. So I'll just still have 6 divided by 2, right? So I've resolved the exponent. Now I can go further in PEMDAS, right? Maybe I should do this every time, right? We have resolved, there were no parentheses, and then we resolved the only exponent. So now we're looking at multiplication and division. Now, this is part of what I don't like about PEMDAS, because the way it's written makes it seem like multiplication goes before division all the time, which is not the case. Multiplication and division basically are handled at the same time, reading left to right. So this multiplication is going to happen before this addition because it's on the left. If the order was swapped, if this guy was like over here, right? If we had 6 divided by 2 plus 2 times 25, then the division is technically supposed to go first. You do left to right, whichever one appears first. Okay, so that's another thing about PEMDAS, where it can be slightly misleading. I actually prefer the acronym PIMA, with the understanding that division is a type of multiplication and subtraction is a type of addition. This makes it more clear that multiplication and division go at the same time, and addition and subtraction go at the same time. Anyway, in this case, that doesn't trip us up, so it's fine, but something to be aware of in general. So next, I'll do the multiplication. It needs to go before the division, but I can do both in this case because they don't interact with each other. This is happening over here. This is happening over there. The plus happens last. So again, I can do the multiplication or division. The order doesn't matter in this case because they don't interact with each other, okay? So I can get 50 plus 3 and get 53, okay? Moving along. My tendency is to like wait for questions or something, but of course, it's not a live class, so I'll try to remember not to do that. Okay, so again, PEMDAS, I need to deal with parentheses, then exponents, then multiplication and division together, and then addition and subtraction together. So in parentheses, right, I have to do whatever's in parentheses first, so I'm going to do 4 plus 5 makes 9. So I'll have 9 squared divided by 3. 9 squared is 81. Divided by 3 is 27. Okay? Okay, moving along. So this one is a little bit more complicated, and we're still following PEMDAS. Okay, so it might not be obvious what happens first. One thing to point out is that the difference between brackets and parentheses is it's just like it shows the layers. So this bracket goes with this bracket, and this parenthesis goes with this parenthesis. They really are kind of doing the same thing, but having them done in layers makes it easier to read. So you can tell, oh, the open parenthesis and the closed parenthesis goes together. Or go together, the open bracket and the closed bracket go together. So it's showing you the layers more clearly. If the problem were written different, like if it were written out as like this, -2 times parentheses 16 divided by bracket 8 minus 4 bracket squared parentheses squared, that would be literally the same thing, because the choice of, when you're talking about grouping, like for arithmetic, just the grouping, the difference between parentheses and brackets is just that's kind of a style choice, I guess. It's however you want to write it. So basically, by default, you just use the curved parentheses. But when you've got a bunch of parentheses going on and you want it to be a little bit clearer, you can choose one layer to be brackets instead, and that just makes it easier to read. But that's a presentation choice, not like a math difference. Later on, you'll find that, yes, when we deal with intervals later on, I guess later on in this video, brackets and parentheses are different, but generally speaking, like for arithmetic, they're not really different. They just show layering. Anyway, so we have 2 layers of parentheses. So I've got this in parentheses, and I've got this in parentheses. And you do the inside first. So I have to do the 8 minus 4 before I do anything else, okay? So, yeah, so -2 times 16 divided by, well, 8 minus 4 is 4 squared, brackets, squared. And then I can do 4 squared. So -2 times 16 divided by 16, right, squared. And by the way, this is another case where PEMDAS is negotiable. If I want to apply this exponent to both of these and get 256 divided by 256, I actually can do that. There, like I said, PEMDAS is more like a recipe that always works, but you can go off script. So there are other properties of exponents that we'll see more of as we go along, probably down here. We'll see some of them. So if I wanted, I can do the exponent out of PEMDAS order if I'm confident in what I'm doing, okay? So again, just want to stress, PEMDAS is like your recipe book. You just follow it and it'll always work, but you don't have to always follow it. There are exceptions, and if you know what you're doing, you can go off script. Anyway, so now I can work inside the parentheses or the brackets, same thing. So different types of parentheses are different layers of the brackets, or of the parentheses rather, and sometimes use brackets. So of -2 times, and I guess this is like 1 squared, and I could have dropped the brackets at that point. And of course, 1 squared is 1, right? So this is -2 times 1, which is just -2, okay? So that's basically how PEMDAS works. And when in doubt, use a calculator if you need to at times, of course. But understanding the order in which exponents and parentheses apply is something that's going to show up over and over and over throughout this class, and then also show up a whole heck of a lot in the calculus class. Okay, let's keep moving. Oops, sorry. Okay. Also, this app I'm using, this is it's called Notability. It's like if you have an iPad and you want to use it, it's actually pretty good. It's not expensive. It's like $10. And there's also like a premium version, but I don't use it. So Notability, it's pretty good. They recently changed the layout, so I might struggle with the interface a little bit. Just FYI. So here is simplify each exponential expression. So there are a bunch of different properties of exponents. The way I think about algebra and arithmetic is it's kind of like you have a big bucket of tools, and sometimes the tool you need is at the bottom, and there's a lot of them, so you can have to dig around until you find it. So one of the properties of exponents is if you have something like, well, I mean, I guess I could just say it here. I'll give the generalization afterward. When you have a product of 2 exponential expressions, an exponential expression is one in which you have a number raised to another number, right? That's an exponent. And either one could be a variable. We'll talk more about that later. When the 2 bases are the same and you're multiplying, you can add together the exponents, okay? So like this will become 4 to the 5th power if I want to do it that way. Also, when you have a negative exponent, that means you're really dividing, okay? It might be hard to see why that is, but basically this negative exponent means we're really dividing. So I think for now, rather than me going for 20 minutes explaining why and going through the theory of why it is like that, if you want to see the why for some of these things, then send me an email and I can explain maybe via email, or we can go on a Zoom call or something. Like I said earlier, I don't want to go off on tangents at every problem explaining concepts that maybe you guys don't need explained. It's not a live class, so I'm not going to spend a whole lot of time doing that. I will try to catch myself and not do that. But basically, these two combine, so I get 4 to the 5th power divided by, and this one I'm going to leave as is for now. Which room do I have? Yeah, that's fine. I don't want to run out of room too quickly, but I'll leave it as is for now. We'll do one thing at a time for the moment. So I'm going to rewrite this in my next step using a fraction. 4 to the 5th power divided by 1 over 4 to the 4th power. So that negative exponent means that you're really dividing the rest of the expression. So the 4 to the 4th power really is in a denominator, is what the negative exponent means, okay? Now, as you might recall, when you are dividing by a fraction, you can do the keep, change, flip pattern. So keep, change, flip, right? So if you have, like, say 2/3 divided by, like, I don't know, 3/5 or something like that, right? Then you can turn this into a product. 2/3, you keep the first fraction, times you flip the second fraction, and then you proceed from there. So you get 10/9 when you multiply that out. So over here, I can do kind of the same thing. I keep the first thing, I change the division into a multiplication, and then I flip the second thing, it being a fraction, right? So this will be 4 to the 5th power times, well, it's going to be 4 to the 4th power divided by 1, right? Which I'll write like this because I'm kind of running out of space here. 4 to the 4th power over 1. But, when you're dividing by 1, you don't need to write that, right? Division by 1 is just, like 7/1 is just 7. 10/1 is just 10, right? So this 4 to the 4th power, I can just write that as 4 to the 4th power. I don't need the over 1. And then I can do the same thing like we did up here and combine the two expressions. Since the bases are both 4, this is 4 to the 9th power. Okay? Now, if we want, I can't do 4 to the 9th power in my head. I mean, I guess if I thought about it, maybe we could, because it's you just keep doubling your number. Maybe we'll get there. At this point, I would just leave it like this. Yeah, right answers with positive exponents. So this doesn't want us to get a calculator and work out what's the big number, which I guess would be, I don't know. It's gonna be like 500,000 ish. Like it's kind of a big number. Like it's the ballpark size. I'm gonna leave this as 4 to the 9th using positive exponents. Okay. So I've simplified it as much as possible without needing a calculator. That's the key thing here. Whatever you can do without a calculator, just using properties of exponents. Okay. And then number 6. Okay. So one of the properties of exponents is that when you have an exponent outside parentheses, and inside parentheses is only multiplication or division. No addition, no subtraction. Okay, what we're about to do doesn't work if there's addition, then it's more complicated. But when you have no pluses or minus, it's just something times something else inside the parentheses. What you can do is you can apply the outside exponent to each of the inside exponents. What do I mean by that? Well, basically, this is going to be the same as b cubed squared times c to the 4th squared. Okay. And that requires another property of exponents. Whenever you have something that's like exponent parentheses exponent, you can multiply those two numbers to get the new exponent. So this is b to the 6th power. Try to make the b's and 6's look different. Okay. Sorry. My handwriting's not the best. Times c to the 8th power. 4 times 2 is 8. Okay, so this is simplified as much as possible without, b and c are not numbers or letters, right? So we can't use a calculator, but simplifying as much as possible, right? So in general, like with this one here, if you have something raised to a numerical power times another expression with the same base raised to a numerical power, you can add together the exponents. Okay. If you're dividing, which we might see that later, a to the n power divided by a to the m power. So you have a fraction where the top is an exponential expression and so is the bottom, but the bases are the same. Then you can subtract the exponents. Okay. So that's what I was doing right there. Here it's a little bit different because if you have some expression, some exponential expression, right? And then parentheses and another one, right? This is what we're doing right here, okay? You can multiply the two exponents together, okay? And the reasons for that go back to what an exponent even says. And again, I don't want to spend a whole bunch of time talking about basic concepts that some of you will already understand. So if this is something you need clarification on, then send me an email. We can set up a Zoom call so I can clarify that for you. Anyway, so that's number 6. Number 7. So the bases are all y. I'm going to do that thing we just talked about right here. The exponent here can multiply with this one, okay? And then also we're going to do, in a separate step, the same thing that we did up here, where a negative exponent means that I'm really dividing, okay? So this will be, we do it in 2 steps. I'll do both of them at once. So this first guy here, I'll rewrite the negative exponent using a positive exponent. That's a y, not a 4. Okay, and then this one, I'll multiply the 2 and the 3 to make 6. Okay, and that's a y, not a 4. Now, I'm multiplying these, and you can think of the y over 6, or sorry, y to the 6th power, rather, as being a fraction as well, with 1 in the denominator, and then I can multiply the 2 numerators together and the 2 denominators together. So I get y to the 6th over y to the 5th. There's actually more than one way to do this one. I think it'd be worthwhile to look at the other way, because the other way might seem simpler for you. Okay, and then like I just talked about, when you are dividing two exponential expressions where the bases are the same, you can subtract the exponents. So this would be y to the 1st power, because 6 minus 5 is 1, and you don't have to bother writing that 1. If the exponent's 1, you can leave it off. Okay, by default, if I write 5, this is 5 to the 1st power. By default, you don't have to put the 1, but you can. Anyway, that's one way to do this one. Another way, maybe doing this was a step in the wrong direction. What do I mean by that? Well, maybe instead, I'll say, okay, well, this is y to the negative 5th power, leave that as is, times y to the 6th power. So just using that property of exponents where you can multiply the two exponents, right? The parentheses are separating them. You can multiply those exponents together. Well, then I can add the exponents together. Negative 5 plus 6 makes 1. And then I can leave off the 1. So instead of doing this in like 3 steps, I can do it in 2 steps. So there's frequently more than one order that works, and whichever one seems obvious to you, you just go for it. You don't need to worry about doing the most efficient process every time. As long as you're using exponent properties and simplifying things, then that's what matters. You don't need to do it the most efficient way every time. Anyway, let's go look at number 8. So with this one, w to the 0 power is just 1. Is the first thing I notice. So this is just 1. So I don't really need it to be there anymore. So this is really just x to the 5th power, the negative 2 power. I can multiply the exponents together, and I get x to the negative 10th power. And then because the directions say use positive exponents, I'm going to rewrite this as 1 over x to the 10th power. Okay. And I should point out that what counts as simpler is there's some subjectivity. Like you could ask which of these is actually simpler, and I would say that the top one with the negative exponent is more simple in sort of a literal sense, and that there's fewer symbols, but the directions say use positive exponents. So the reason for that is that it's not like there's an end goal of what is actually simpler. It's just that we want you to have practice and familiarity with manipulating exponents using these properties, so that when you need to do something else with them, you're aware of what's available, like what simplifications can be made. And it's not that there's always a single correct, most simple version. It's just there's a list of options. Like I mentioned, that bucket of algebra and arithmetic properties that you have to kind of sift through and find the one you need. Well, it's a big bucket, and there's lots of properties. And part of becoming more skilled at algebra is just being familiar with all the tools in your toolbox and knowing how to apply them and when to apply them. And then just when you're presented with something to complete some problem, you just start trying stuff. You just pick one of the tools and try it out and go from there. Anyway, let's move along. So this one. Now, this uses something that we've kind of already talked about, but there's more than one version of it, I guess. So, yeah, there's probably like 3 or 4 different ways to start this one. I think what I'll do, though, is, yeah, let's do this. So, when you are, yeah, it's a variation on what we just talked about a minute ago. So, if you have, a hold on, sorry, getting ahead of myself. This is actually a different property. So if you have a fraction with an exponent applied to it, okay, you can apply that exponent to the top and bottom separately if you want to, okay? And that's what we're going to do over here. So I'm going to rewrite this as x to the negative 3 power, that raised to the negative 5 power, over y squared, that to the negative 5th power. So I'm just applying the exponent to the top and bottom individually. then what I can do is I can use that property that we talked about earlier, where when you have an exponent and then parentheses and another exponent directly stacked on top of it. And what do I mean by that? We'll talk about that in a second. When you have a base, exponent, parentheses, exponent, then you can multiply the exponents together. So I'll get x to the 15th power on top. Wrong tool there. There we go. Sorry. Like I said, still getting used to this interface. So x to the 15th power over y to the negative 10th power. And then this negative exponent here, this tells me that I need to, basically when you have a negative exponent, as in here, okay, this tells you that you're really dividing that base of 4, and so it moves into a denominator, okay? If what you have is already in a denominator, you move it out of the denominator. So this y will move up next to the x, and its exponent will change from negative 10 to positive 10. So this is x to the 15th power times y to the 10th power, okay? And that's as simple as possible, positive exponents. So caveat, what I was talking about this guy here. So if you've got something raised to some numerical power, parentheses, and then another numerical power, you just multiply those exponents together, okay? But what if you had something like this? What if I had like 1 plus x cubed? In fact, let's do x squared cubed, like this, okay? This is not 1 plus x to the 6th. And the reason is this, this plus 1 is in the way. It prevents that from happening. Notice how there's no plus anything here. If there's a plus something, like here, that gets in the way and that property doesn't apply. So the way to simplify this is more complicated. You can't just use properties of exponents. It's something that we'll get to a little bit later. Like, how would you simplify this? That's for later in the class. I just want to point out that this property here that we used right here, this relies on the base in parentheses not having other stuff next to it, like a plus 1 would interfere with that property, okay? And again, you can always ask for like assistance via like Zoom office hours to get more clarity on these things if you need it. Okay, moving along. So simplified each radical expression. For one thing, you might say, oh, just throw it in a calculator. Well, kind of. We're going to go over the properties of exponents that are of roots rather, that will allow us to simplify this. And then we'll also talk about like, how would you do this in a calculator? So the first thing, which we'll do this without a calculator to start with, is every root is also an exponent. So the square root of something can be represented as that something to the 1/2 power. Every root is a fractional exponent, and it might seem a little weird, but an exponent tells you how many copies of something to multiply together, right? Like 3 squared or 3 cubed. This tells you, oh, I have 3 times 3 times 3. The exponent tells you how many copies you have. Well, if I have something that when I square it, when I multiply it by itself, right? Root a times root a, this is a itself. That's what the square root means. The thing that when you square it, you get a, right? So it happens to turn out or to work out that if you put a 1/2 exponent here, then a to the first power, well, that follows that property we talked about, where if you have two exponential expressions multiplied together and the bases are the same, the exponents add together. So 1/2 plus 1/2 makes 1. And it just turns out that fractional exponents do the thing that by definition a square root does. A cube root would be a 1/3 power. So like if you have like the cube root of 8. This is the same as 8 to the 1/3 power. And if you plug this one in your calculator, you'll get 2. And if you plug this in your calculator, you'll get 2. They're equivalent, okay? So looking at this one, what I'm going to do is I'm going to think about how can I simplify this, because all the properties of exponents are also properties of radicals, because every radical is an exponent, essentially. It's a fractional exponent. So all the same properties apply. So just like when I have, you have something like, well, I'll just show it with this one. We can speak about the generality later. Basically with this one, I'm going to want to look at, well, what what do what can I do to break up this 196, right? And you might notice that this is 14 times 14. And maybe it's not obvious, of course, but you might notice this is 14 times 14. So this is the square root of 14 squared. Okay. And you can either say, oh, well, the square root of 14 squared, that's just 14. You could say that, right? Maybe it's clear, maybe it's obvious. Or you could say, well, let's rewrite this with a fractional exponent. And then use that property that says that when you have an exponential expression, parentheses, another exponent layered on top of that, you multiply, wrong tool there, you multiply the exponents together and you get 14 to the first power. And then you don't need the first power, you just leave that off, it's sort of implied, and you get the same thing, okay? So that's one way to do it, is to think about the number, see how you can break it into pieces. When the number is 196, maybe that's not super difficult, but that is kind of a big number. You might just throw it in a calculator and see what you get, but also we need to understand what properties are at work that make this happen. Number 11. Now this is going to be harder because we have bigger, messier numbers, and we have a negative as well. So whenever you have, like, say, the fifth root of something, what you want to do is this. The fifth root of 32. Let's start with positive 32, and we'll deal with the negative in a second. Okay, this equals some question mark. What it's saying is 32 is equal to that something, whatever it may be, to the fifth power. Okay, so what would you multiply it with itself 5 times to get 32? And if you took, like, computer science in high school or something, you might know right away because it's a power of 2. 32 is 2 to the fifth power. Okay. And if you took computer science in high school, you might just have memorized that from seeing it enough, right? Now there's a negative exponent, so we have to be careful there. Whenever you have an odd root, not negative exponent, sorry, a negative numerator, my mistake. Whenever you have an odd root, the root is 3, 5, 7, like that, this minus sign can just move out in front, okay? When you have an even root, like if the index of the root is 2 or 4 or 6, then that doesn't work. You can't have an even root of a negative. So, even root, let's see. So an even root of a negative number is not defined. And we might talk more about why that is later. Basically, an even root of a negative number requires what are called complex numbers. And complex numbers aren't used in a first semester calculus class. So we don't need it for the calculus class later. And especially in business applications, this is mathematics for business. In business applications, complex numbers don't really show up unless you're doing, like, some really high level economic theory, which is kind of math heavy, right? Just for, like, undergraduate level business applications, you just don't need complex numbers. They just don't show up. So for this class, we don't really deal with those. We're just going to say, yeah, we don't deal with complex numbers. So since this is an odd root, the minus just moves out in front, okay? Also, whenever you have a root of, whenever you have a root of any index, just like if you have, whenever you have a root of any index, but I'll do square root specifically here, you can apply the root to the top and bottom separately, just like with exponents, because remember, every root is an exponent, it's a fractional exponent, so you can apply it to top and bottom individually. So for this one, the first thing I'm going to do is I'm going to move the minus sign out front. Okay, that's step 1 for me. Oftentimes, the order of the steps is optional. That's what I'm going to prefer to go with. Okay, so this is going to be the negative of the fifth root of 32 over the fifth root of 243, like we just talked about. You can apply the root separately to the top and bottom. And sorry if my handwriting's a little bit messy. Try to keep it neat. So like we talked about, the top, this will be 2. So this is negative 2 over. And if you think about what do I raise to the fifth power to get 243, that's not going to be obvious. One thing you can do is get your calculator. And if your calculator will do this, well, okay. But, like, think, okay, basically what we're trying to answer is, we're trying to answer something to the fifth power equals 243. Again, trying to keep this neat, okay? And just start trying stuff in your calculator. Try 1 to the 5th power, try 2 to the 5th power, try 3 to the 5th power, try 4 to the 5th power. Just try things until you find it, and you'll find out that 3 is the result. So 3 to the 5th power is 243. Okay. So that's 3 on bottom. So that's our answer. Negative 2/3 would be the simplification of the 5th root of negative 32 over 243. And again, this is all stuff that a calculator can do, but we're going to need to understand the properties so that later when we have variables involved, we can still manipulate things and shove the symbols around using the algebra properties or the arithmetic properties of exponents. But we have to sort of pretend we don't have a calculator that will just do it for us. Okay, so I ran into some technical difficulties. Hopefully they don't continue to be a problem, but we'll just keep moving from here. Okay, so number 12. So with this one, there arises a small complication because we have an exponent of 3. Before we did not have exponents inside of these roots, right? No exponents here. I mean, we kind of did. I created one, and then no exponents here, unless you want to consider that I created one. So up here, like this is a case where, well, there aren't just numbers. So if you try putting this in your calculator, you might not get something useful because, well, it's not all numbers. So what I'm going to do is I'm going to use a property of roots that I don't think we've used yet. So if you have like the square root of some product of two things, this can be rewritten as the square root of the two things multiplied together. Okay, so you can apply the square root individually to the two pieces. So with this one, I'm going to split up in the following way. So 49 p cubed, I can write this as 49 times p squared times p, right? So this is going to be the square root of 49 times the square root of p squared times the square root of p, all right? Now, the square root of 49 you might recognize as 7 because that's not a very big number. Maybe that's obvious, maybe not. Now, the next part we're going to do, it might seem real simple, but there's actually a lot happening under the hood. So whenever you are finding the square root of something, remember what this symbol says. This is saying if you have the square root of, wrong tool there. If you have the square root of something, so s, this means that this is the something that when you square it, you get the thing inside the root, okay? So the square of the square root of s is s. Like by definition, that's what square root means. It's the thing that when you square it, you get that thing, okay? So this guy here, this is saying, what do you start with and square it in order to get p squared? So in other words, this is saying something squared equals p squared. Well, the something that you would square in order to get p squared, that would be p, okay? So times p times the square root of p. Now we have to be a little bit careful. There's a caveat here. So let me go off on a little bit of a tangent there. If I start with 3 and I square it, I get 9, right? If I square root that, I get 3, right? Everyone with me? 3 squared is 9, the square root of that is 3. If you start with -3 and you square that, well, -3 squared makes 9, right? And if you square root that, you don't get -3, you get 3, because the square root of 9 is 3. So when you start with some number, and you first square it and then square root it, you don't always simply get the number you started with. If the number you started with was positive, well, then you do. If the number you started with was negative, you get the absolute value of it. So more generally speaking, the square root of a squared is not a. It's the absolute value of a, more generally. Now over here, and I don't know, I don't remember, did it give us this caveat? It did not. That's okay. We can still do this, but we have to understand that we made an assumption right here. We made an assumption. We assumed that p is not negative anyway, but that's okay. Because if p is negative, we talked about how you can't have an even root of a negative input value because that runs into complex numbers, and we don't deal with that in this class. So because there's another p floating around without a square on it, and we have the square root of p as part of our expression, that means p is not allowed to be negative anyway. So we are making sort of an assumption by doing this, but that assumption is totally fine because p has to be positive or 0 anyway, because you can't have the square root of p if p is negative. So p is not allowed to be negative anyway. So we can write this a little bit more compactly as 7p times the square root of p. Well, that's not neat at all. Hold on. 7p times the square root of p. Okay. Simplified a little bit. So basically, you break up the radicand. The thing inside the radical symbol is called the radicand. Sorry, some terminology there. And you can break the radicand up into pieces where each piece is itself something you know how to unsquare or square root. So 49, square root of that is 7. P squared, square root of that is p. And whatever's left just stays in the root and it doesn't get simplified because it's kind of stuck there. And that's going to happen sometimes. Okay, hopefully that's clear. Moving along, this one has a fraction involved. So we're hopefully going to be able to cancel some stuff. So what I'm going to do is, I guess there's a couple of ways to deal with this. I'm going to try to basically reduce the radicand in both of these. When you're reducing the radicand, what that means is you want to move stuff out of the radicand. So like up here, the 49 ended up moving out and becoming the 7. Some of these p's moved out and became this p out here. So when you're reducing the radicand, you want to remove stuff from that radicand and move it outside the root, in front typically. Okay, so that's what we're going to do. We're going to reduce this, so the denominator. So I want to break up the radicand 32n cubed into pieces, each of which I know the square root of, or I can figure it out without too much trouble. Okay, so the top, I'm just going to leave it as is, 4 square root of 2 times n. 2 is just like it's the smallest even, well, smallest. It's the smallest positive even number. You can't break that down into smaller pieces, right? Like it's not like the 32 we had earlier. And then n doesn't have an exponent. There's one copy. So that 2 and that n are just going to sit there. But this, I can break this up. The 32 can be broken up into like 8 times 4 or 4 times 4 times 2. There's a couple ways to do that. I'm going to break up the radicand on bottom. This I'm going to write as 16 times 2, because 32 is 16 times 2, and 16, I know the square root of that, times n squared times n. So I'm identifying these different pieces that I can find the square root of without much trouble. And then the 2 and the n that are left over will stay there. So I guess we'll use some vertical room. Is that okay? Yeah, that's fine. Okay, I hope so. Anyway, so the top will be just what it is, 4 times the square root of 2n. Okay, this 16 here, when it moves outside, I form the square root. So 16 will turn into 4 when it moves outside. And the n squared, when it moves outside, it will lose the square, lose the exponent, and become just n. Kind of like with the p in the earlier one. So this will be 4 times n times the square root of 2n. And what I can do now is I can reduce my fraction. The 4's on top and bottom can cancel. But then also, the square root of 2n, all of that can go away. And so all I have left is I have 1 over n is all that's left. Everything else canceled out. Okay? All right. So moving along, did I miss something? No, there's a new problem type. Okay, so factor each polynomial completely. Okay. So you've probably learned factoring in high school at some point, and there's different approaches. There's something called slide and divide you may have learned that has its drawbacks, but it works if you apply it correctly. Some people have what's called the box method. There's just different ways to do this. So I'm going to point out the things that the way that I would do it, the things that I think are the most useful approaches. So with this one, I noticed that this one allows a bit of a shortcut, because this number here and this number here, they're both squares, right? 4 is 2 squared and 9 is 3 squared. So I can factor each of these as to like 2 times 2 and 3 times 3, right? 4 is 2 times 2, 9 is 3 times 3. More specifically, what I can do is this. I can write this as, this is 2m squared okay? Because 2m times 2m is 4m squared minus 3 squared, okay? When you have what's called a difference of squares, some square minus another square, and they won't be the same because then the total would be 0, but two different things in parentheses, both squared. If you're subtracting them, there's a pattern to that. So a squared minus b squared, that's the sort of generic pattern. This will always factor as a plus b times a minus b. Okay, and again, I'm not going to go off on a tangent of why is it that that's correct. I'll leave that for someone to ask about if they need to. But that's just a formula you can basically memorize, and it always works. So basically, when you factor something or when you rewrite something as a difference of two squares, you basically take the two things inside the parentheses and you'll have their sum in parentheses times their difference in parentheses. So this will be 2m plus 3 times 2m minus 3. Okay. And we need to talk about FOIL a little bit. Okay. So FOIL stands for first, outer, inner, and last. This is basically a shortcut for multiplying, or in other words, distributing what are called binomials. So whenever you have a thing with two parts, something plus something, times another thing with two parts, something plus something, or minus, then FOIL is like the pattern to multiply this out. So this first part means you're going to multiply this guy with this guy, the first thing in each pair of parentheses. Okay, you're going to multiply this together. So 2m times 2m, that's 4m squared. Okay, and then outer, you're going to do the two outer things that are furthest from the center. So 2m times negative 3, that makes negative 6m. And then inner, so there'll be the two things closest to the center. 3 times 2m makes plus 6m. And then last means multiply the last item in each group of parentheses. So plus 3 times negative 3 makes negative 9. And you might notice that these two terms are equal, except for one is plus and one is minus, so they cancel. And we get 4m squared minus 9 when we FOIL that out, which is what we started with. So when you're factoring, this is the process of factoring using the just noticing that we have a difference of squares. Okay, and I'm foiling to check that I got the right answer. So whenever you're factoring, you can use foiling to double check that you got the right result. Okay. Now this one has a lot going on. This one's going to be a bit of a pain because the numbers are so big, but that's just going to happen sometimes. So there's a couple ways to do this. If we were super lucky, because these are all kind of big numbers here, right? 90, 181, negative 181, and 90. If we were lucky, maybe we'd be able to factor out a 9 or a 10 or something from every term. So when you have big numbers like this, the first thing to check for is there a number that I can factor out of every term. In this case, no, 181 is not. 181 and 90 don't share any common factors. 181 is not divisible by 3, 2, or 5, so they don't share factors. So that's not going to work. So we need to use what's called the AC method. Again, there's several methods for this. So if you've learned some other method, that's totally fine. But I'm going to show you what's called the AC method. Okay. Now the AC method is called this because the generic format for what's called the quadratic expression, a polynomial with degree 2, the exponent is 2. The generic format is ax squared minus bx plus c. So this first number, this is called the coefficient that corresponds to position A. That is a mistake. That must be a plus. Sorry, the generic format doesn't have any minuses in it. Sorry about that. So then B is negative 181 and C is 90. What we're going to do is, how much horizontal room do I have? Oh, quite a bit. What we're going to do is I'm going to multiply A and C together. Okay, so A times C, this is going to be 90 times 90 is 8100. Okay. Now what I want to do is I want to pick some way of factoring 8100 into two numbers such that those two numbers add up to this middle coefficient of negative 181. Now, we're lucky this one I see what to do, but I'm going to start with a combination that doesn't work just to show what's happening. What do I mean by a factorization that adds up to negative 181? Like, what does that mean? So what I want to do is look at different ways to factor 81. Like this is 810 times 10, right? 810 times 10 is 8100. Now, so because my AC value is positive, then these are either both positive or they're both negative, okay? And I want to look for the combination that adds up to make that negative coefficient negative 181. These two make negative 820. That's much too big, not even close, okay? So that won't work. And I could just start trying other things. Like I could try, I guess 909, right? 900 times 9, that makes 8100. Now, if I leave them as positive and add them up, I don't even get a negative value. I just get 909. It's not even negative, and this is supposed to be negative 181. So I'm definitely not going to be using positive values. And if I make them negative, well, when I add them up, I get negative 909, which is even bigger. It's worse. It's further away from what I want. So what I need to do is sort of trial and error. Maybe you already see what to do. If I do 81 and 100, okay, if I make them both plus, well, then I'm going to get 181, which is not the right sign. I need negative 181. So if I make them both negative, okay, then I get negative 181 for their total. Now, remember what's happening is I need the two numbers. Sorry, let's change the color here. You need the two numbers that multiply to make this, but add up to make that. Okay, and we'll see why that works in a second. Okay, so no, I don't want to undo that. I want to erase this. So I'm going to take that combination, negative 81 and negative 100. And what I'm going to do is I'm going to break up this term and write it as two terms. I'm going to write it as negative 100x minus 81x. And then we'll go from there and you'll see why this works. So we've got 90x squared minus 100x minus 81x plus 90. Okay, so I've broken up that middle term. The next step is to focus on each pair. So like these two terms and these two terms, and I want to look at each group separately. So for temporarily, ignore this, focus on this. And I want to look at, well, what is the common factor of both terms? What can be factored out of either one? Okay. Sorry, fiddling with my setup here so that hopefully we don't run into more technical issues. Basically, the Zoom call ends if it doesn't detect any activity. So anyway, so you might have had a second to think about what is a common factor here. Well, both terms have an x. The first term has two copies of x. The second term has one copy of x. So they both have one copy. I'll factor out one copy. Also, the two coefficients, 90 and 100, those are both divisible by 10. So I'm going to factor out 10x from both of these. Okay, so 10x, I'm going to factor out, and it's kind of like you're dividing that out. So then I need to take this term, and if I remove a 10 by division, right, that means I'll have a 9 left. 90 divided by 10 is 9. Okay, I'm not going to subtract 10 and get 80. No, I'm dividing 10 and getting 9, and I'm dividing out 1x and leaving a copy of x. So I have 9x. Okay, and if I were to multiply them back together, 10 times 9 is 90, x times x, 10 times 9 is 90, x times x is x squared, I would get this again, okay? So I'm factoring, which is the opposite of distributing, so I'm working backwards through distributing, through multiplication essentially, which is sort of like I'm dividing. So then I want to look at the other term and say, okay, well, if I remove a 10, and not through subtraction, not through addition, but through division, if I take out a 10, that 100 will become a 10, right? 100 divided by 10 is 10. And if I remove an x, that x gets just moved out front. X divided by x is 1, and so the single copy of x gets removed. So I have minus 10 left over. And again, if I multiply this back, 10 times 10 is 100, I'll get negative 100x. Okay. So now let's ignore this temporarily and focus on this part. So looking at these numbers, right? Well, are these terms rather? They don't both have x, right? The first term has x, the second term does not have x. So they don't both have it. But 90 and 81 are both divisible by 9. So I'm going to factor out a 9. Now there's something else I'm going to do, which might not be clear why, but you'll see that it works out. I'm going to factor out a negative 9. Okay, so this will be minus 9 times, and I have to factor a 9 out, a negative 9, right? So when I divide negative 9 out of this, I'll get 9x, right? I'm removing the minus. I'm removing one copy of 9, so 9 is left over. 81 divided by 9 is 9, and then the x is still left as well. So I get 9x, and then when I factor a negative 9 out of here, okay, I'm dividing by negative 9 to move it out front. I have a negative 10 left over. Okay, now let's go back to considering all of these terms together. Okay, that's the result of one step of the factorization. Notice, though, that the inside parts of these parentheses are now the same thing. This is the reason the AC method works, is if you follow this process, you get the right combination of numbers that breaks up in that way, then at this point, these two things will be the same. And what you can do is say, well, kind of like how up here, let's clean this up a little bit, kind of like how up here, I noticed that 10 is a factor of both of these numbers, 90 and 100, so I factor out a 10. Whatever's present in both, I can remove and put outside of parentheses. So now I have it to where this is the repeated factor. 9x minus 10 is a factor in both terms of the larger expression. So I'm going to put the 10x and the negative 9 together. Oops, wrong tool there. I'm going to put the 10x and the 9 minus 9 together in their own parentheses. This goes here, this goes here, and then the 9x minus 10, that goes off by itself as its own factor. Kind of like how the 10 that is present in both of these as a factor goes out front, and each of these loses a copy of 10. The very same way, the 9x minus 10 that is present in both gets removed outside some parentheses and goes at the end, and these parentheses here are grouping together the 10x and the 9, so it's like these two are still there. They're represented by the single copy, and if you were to redistribute this out and FOIL it, then you would get the original expression. So if we go and FOIL this, okay, then we should get this right here. Okay, I'm not going to do that right now because this video is already going to be it's going to be long, and I don't want to spend a lot of time on things that maybe you all don't need. So if you should on your own FOIL this out, this result, and make sure that you get this thing just for your own benefit. You see that, yeah, it does seem to work that way. Okay. All right. Well, moving along. Yeah, here, this one. So the fact that the letter is P and not X doesn't really matter. Just don't worry about that. Sometimes, if you're lucky, the numbers are simple enough or small enough that you can just kind of look at it and guess and check. So like I could try to say, well, I know I'm going to have two pairs of parentheses. I'm going to have some stuff times some stuff. And if I FOIL it out, I'll get 2p squared plus 9p minus 18. And if I want, I can try to guess. I go, well, maybe this is 2p here, p here. And maybe this is like, I don't know, net minus 3 plus 6, something like that, right? Like that's a possibility. And, which one is it? I don't know. I kind of was guessing. I think this might work out, but I was kind of just guessing at what might work. So I got the 3 and the 6 from the 18. And since the 18 is negative, I made sure that one of them got a minus. Now what I can do is just FOIL this out and see if I get the right thing. Okay, so remember FOIL stands for first. Probably want to use the right pen. First, oops, we're needing the first, outer, inner, and last. Okay, so the two first things is going to be 2p times p. So that's 2p squared. Okay. And then outer is going to be the two outer things. So 2p times 6 makes 12p, so plus 12p. And of course, keeping track of any minus signs you might have lying around. Okay. And then inner means the two inner things. So negative 3 times p, negative 3p. And then last, negative 3 times positive 6 makes negative 18. And then if you combine like terms, 12p minus 3p, 12p minus 3p makes 9p, which is what we're supposed to get. So this is the correct factorization. So if you're lucky and the numbers aren't too difficult, you can just kind of guess and check, and that'll work sometimes. Like with this one over here, I think guessing and checking could have worked, but the numbers are bigger. That does make it harder. I think when the numbers are bigger, just use the AC method or whatever method you've learned. If the numbers are small, maybe you can guess and check. I think with big numbers, this is less reliable because there's so many options. How are you going to guess it? I mean, not that you can't, just I think it's the harder way to do it. Okay, moving along to this one. This is one where I probably would not want to guess. So I'm going to use the AC method. So I'm going to have the first number times the last number, so negative 49. Okay. So when I make my factorization, I need to make sure one number or the other is negative, but not both. Okay. So I could have something like well, negative 1 and 49, those multiply make negative 49, but when you add them up, you get 48, which is not what we wanted. In fact, you know what? I think actually this is a typo. Yeah, this file has a typo. This is supposed to be 48. Let's do this. Is that going to work? It works sort of. We'll take that as good enough, I suppose. Yeah, it's supposed to be 48. Yeah, sorry about that. That's just a typo in the file that never got fixed. Okay, so basically we just use the AC method. I wonder if it would be useful to like work the problem as is with 78, but it doesn't factor in a nice clean way. You get stuck. So let's just go with this. Anyway, so now I know the breakup. I want negative 1 and 49. So so I break up the middle term. So this will be 7x squared minus 1x plus 49x. And you might be wondering, does it matter that the negative 1x went first and the 49x went second? Not really. If you swap the order, you end up getting an equivalent answer anyway. So don't worry about which one goes first. It doesn't affect your end result. I'll explain what I mean in a second when we get there. So minus 7. And then again, I'm going to take my two groups. So this group and this group. Okay. From the first group, again, ignoring this one temporarily, from my first group, both terms have an x. And that's the only thing in common, so I'll factor out an x. So I have 7x minus 1 left over. Okay. That's not a very good 7, but yeah, let's go ahead and fix that. 7x. Okay. And then this group, both terms have 7. Like 49 is divisible by 7, 7 is divisible by 7, so I'll factor out as 7. Now, I'm not going to do negative 7, okay, which you could do. Like if we did negative 7, like this, notice how these two are not the same thing. The signs are different. So you only need to factor out a negative if that helps you make the two parentheticals equal. But it doesn't, so I'm just going to factor out 7. So we'll have 7x minus 1, because when this loses a copy of 7, it becomes 7. When this loses a copy of 7, it becomes 1. Okay, and then these two are the same, and I can factor that common factor out, put the x and the 7 together in parentheses. And then the 7x minus 1 will go at the end, outside the parentheses, and this 7x minus 1 is representative of both of these. That's how factoring works. When a factor shows up on more than one term, you put it out in front or at the end and put parentheses, and that represents it being applied to every term in the group. Anyway, that's how that one works out. And if you want to check your answer on one of these, you just FOIL the result that you got, and you should get the original, and that means that you did it correctly. And if you FOIL it and you get something different, well, then you've got a mistake somewhere. Anyway, yeah, so this is the first part of that section. Let's move on to the next part. And yeah, okay. Just looking ahead a little bit. So solve each equation for x. This first module, since it's reviewing stuff, it's like a survey of a lot of different things. So this video might be the longest video that we have for the class. Later ones, in some cases, will be quite a bit shorter than this one. I don't know exactly how long this one's going to be, but so far it's about 45 minutes. So the whole thing might be about 90 minutes, which if you're watching this video, I guess you already know that. Anyway, so solve each equation for x. So when you have an equation that you want to solve, basically you manipulate the two sides of the equation. So you'll do things to both sides in order to shuffle stuff around. So if I want to move, for example, this 3x, I want to move it over to the other side. I have to move it by doing something. I can't just rewrite it on the other side. I need to think about what operation is happening with 3x and how do I move it, okay? What do I do to both sides to move it? Because I need to keep track of, am I subtracting, am I adding, am I multiplying, am I dividing? Because the 3x, when it gets to the other side, it needs to be doing the appropriate thing to combine appropriately with the stuff that's already on the left. So what I'm going to do is I'm going to subtract 3x on both sides, okay? And that will have the effect of canceling this one over here and giving us 4x on the left. And then I can subtract 2 on both sides. And you don't have to write this like I'm doing, where I'm writing the subtraction out. And we're going to run out of space, I guess. So you don't have to like write necessarily this part every time. You can just write the result of it. If that makes sense for you, that's okay. Just you need to, like, basically when you're doing this on like on homework or an exam, do these things one step at a time. Don't try to do 4 or 5 things all at once, because then the grader can't tell what you're doing potentially. And if you make a mistake, like if you're doing like 3 or 4 things at one time in each step, then if you make a mistake, well, how is the grader going to tell what the mistake was if you're doing like 3 things at once? It can be unclear, right? It's hard to suss out what you've done when you're cutting corners and skipping steps. So show your work thoroughly in stuff that you turn in. Make sure you're showing what's happening. Don't just get the answer. Make sure you're showing what's happening. Anyway, now I can divide by 4 on both sides. And I get x equals negative 11 over 4. Now, if I want, I can go plug this back into the original equation and check that my solution actually fits the original by totaling up both sides and making sure that the two sides are equal. I'm not going to bother doing that here, but if, like, on a test, you want to check your answer before you submit it and you want to get full credit, you can totally do that to see if your answer is right. And also later in the class, we'll find that there are some types of equations where checking your answer in the original equation is actually a requirement. For this type of equation, it's not required. It's just a good idea to be thorough. But we'll see that there are times where it's actually required, which we'll talk about when we get to it. Okay, so this one. Now, you might look at this and go, oh, okay, so we're going to subtract 1/2 on both sides, which is not a bad idea. But I think with this kind of problem, what we actually want to do to get started, kind of cramped for space here. I'm going to rewrite the equation, and then what I'm going to do is I'm going to do what's called clearing denominators, because fractions can be kind of a pain. Sometimes you're just stuck with them. They're going to be fractions in math class, right? But there are times where you can sort of avoid dealing with them temporarily, and that can make working problems out a little bit easier, depending. So what I notice is I've got 3 denominators, right? 2, 3, and 3. The fact that 3 is there twice is kind of, I can kind of ignore that. I don't need to worry about the fact that 3 is there twice. So I can kind of ignore that 3 if I want to. And what I want to do is I want to take the least common multiple of all the denominators, okay? And it's not that this 3 shouldn't be counted. It's just that it's redundant because I already have a 3. So I want the least common multiple of 2 and 3, or in other words, 2 and 3 and 3, which is 6. So I'm going to multiply both sides of the equation by 6. And this will have the effect of getting rid of the denominators, okay? So when I distribute this 6, it's going to multiply onto this fraction and make 6 over 2, and onto this fraction and make 6 over 3, okay? Now, I could cut corners here a little bit, but I want to make sure this is as clear as possible, so I'm not going to cut any corners. So this will be 24 over 3, which It pains me slightly to do it that way, but I'll explain. So now I can reduce these. 6 over 2 is 3. 6 over 3 is 2. And 24 over 3 is 8. So the fractions are all gone. Okay, so I don't have to deal with fractions anymore. My answer might be a fraction, but I can defer dealing with fractions until later. So I can proceed with the problem 3 minus 2x plus 8, and we'll proceed with it in just a moment. What do I mean when I say it pains me to do this? Can I zoom in more than that? It won't let me. Okay, so look at this product here. I have 4/3 times 6. Whenever you have a fraction or a number like this, multiplied or divided or whatever with a fraction, you can always think of this as being over 1. So every whole number qualifies as a fraction if you put it over a 1, right? And this might be obvious, this part. I did 4 times 6 to make 24, and then I did 3 times 1 to make 3, right? Well, when I said this pains me to do it this way, what I mean is I tend to prefer to reduce across first. So 3 and 6 reduce to make 2, right? The 3 cancels with part of the 6, and then I get 4 times 2. 4 times 2 makes 8. So the order in which you simplify or combine fractions, there's some choice. You have some choice in how you do that. If the first way I did it makes more sense to you, do it that way. 24 over 3 is perfectly fine. If the second way, where I reduce the 6 before combining and I get 8, I still get 8, right? If that way makes sense to you, then do it that way. Whichever one you think made the most sense, do it that way. They're both fine. For me, the second way makes more sense, but I know for some people the first way makes more sense, and just whichever you think is the clearest, do that. So then we can proceed from here. And I say, okay, now I need to solve this equation. So I'm going to subtract 3 on both sides. And I'll leave that color, that's fine. And so I'll have negative 2x equals 5, and then I can divide by negative 2 on both sides. So we get x equals negative 5 over 2. Some people ask, when you have a negative fraction, where does the minus sign go? Does it go in the top? Does it go in the bottom? Does it go in front? And the answer to that is this minus sign has 3 places it can go. It can go out in front. That's fine. If I want to attach it to the 2 and make negative 2 on bottom, like I had here, that's also fine. If I want to attach that minus to the 5 and have negative 5 on top and positive 2 on bottom, that's also fine. Just this minus sign needs to go somewhere, either in front, on top, or on bottom. You get to pick where. It doesn't really matter. But in front is typically where people write it. But it actually can go more than one place. Okay. Yeah. So there's that example. Okay. So let's go on to this one. So again, this is one where we have fractions, and I want to deal with the fractions first, or at least address them so I can defer actually dealing with them. You don't have to do that. If you really want, you can add these, subtract these 2 fractions by getting a common denominator and go from there. I prefer not to do that. I think it's just easiest to multiply both sides by the common denominator. So basically, you look at all your denominators and look for what is the least common multiple, right? What is the smallest number that's a multiple of 3 and 4 and 12, right? Well, 12. 12 is a multiple of 3. 12 is a multiple of 4, and 12 is definitely a multiple of 12. So I'm going to multiply both sides by 12. Okay. And notice I'm not using parentheses on the right. And the reason is there's a single thing here. If I put parentheses, it's just redundant. I don't need them. But here I do need them, because if I didn't put those parentheses, then it would look like the 12. Oh, sorry, wrong tool. It would look like the 12 is actually only applying to this first one, 12 times x over 3. And then from the way I've written it, the 3/4 doesn't get a copy of 12, but it's supposed to. So those parentheses need to be there, okay? Yeah, so then I will distribute. So this 12 will multiply onto here and onto here. This 12, I'm just going to cancel with that other 12. So I'm kind of like handle these a little bit differently. The left-hand side versus the right-hand side, I'll handle slightly differently. On the right, the 12s just go away. On the left, I'm going to distribute the 12. Over here, just get rid of those. So on the left, I'm going to have 12x over 3 minus 36 over 4, because 12 times 3 is 36, right? Equals 2x plus 3, with the 12s just canceling. And then I can simplify here. 12 over 3 is 4, so this is 4x. Minus, well, 36 over 4 is 9. Equals 2x plus 3, not minus 3. And then I can go proceed from there to solve the equation. So how much room do I have? Yeah, I got room. Okay. So I'm going to subtract 2x on both sides. Okay. So I'll have 2x minus 9 on the left equals 3. Add 9 on both sides. So I get 2x equals 12, and then I'll divide 2 on both sides. So x equals 6. And again, if I want, I can go take that 6 and plug it back in to check that it really is the solution if I want to. Again, it's not required for this problem, this equation, but I can if I want to check that. Okay, so that's all for that. So now this next part says, find the slope in the equation of the line that passes through the given points. Okay, so there's a formula for this, and again, I'm going to probably repeat myself some more on this topic, but I'm not going to go into a big discussion about why things are like this, because it's probably review for most of you. If there's some stuff you really don't get, then we can get on a Zoom meeting and I can explain it to you in more detail. So there's a formula. There's actually two. I mean, I guess there's three. So the first thing is that, let me zoom in more here. So when you have two ordered pairs, x1, y1, and x2, y2, okay? So x coordinate of point 1, y coordinate of point 1, x coordinate of point 2, y coordinate of point 2, okay? Then the slope of the line between them is going to follow rise over run, or in other words, it's the difference in the y coordinates, so y2 minus y1 over the difference in the x coordinates, x2 minus x1. And it turns out that if you swap the order of the top and the bottom, both, if you make the top y1 minus y2 and make the bottom x1 minus x2, that's actually the same thing. When you switch the order of the top and the bottom, all of the, it's equivalent. Nothing really changes, okay? That's because of, well, if you do it with numbers, you would see. So let's actually do that with numbers in a moment. So another formula is, so this is the slope formula, right? Slope. Another one is the, what's it called? The slope-intercept form for a line. Slope-intercept form. So this is y equals mx plus b. And sometimes that format is what you want to use. And there's also the point slope form for a line. Okay, that one is y equals, there's actually more than one version of this, but I'll give the one I know, or I'm most used to. So y equals m times x minus x1 plus y1. And these x1, y1, these are the coordinates of the first point, but it doesn't matter which one you use. So actually, if you use the coordinates of the other point, that still works. You just got to pick one to go with. It doesn't matter which one you pick. Okay, so let's look at doing the slope calculation. We'll use both. We'll first call this point 1 and this point 2, and then we'll calculate the slope, and then we'll do it again with the other order, and you'll see what I mean. So the slope here, well, that's going to be y2 minus y1 over x2 minus x1. Okay, and if I plug in, my numbers, so y2 is 9, and y1, sorry, let's do it this way. y2 is 9, y1 is 4. So 9 minus 4 on top. Okay, and then we'll do 7 minus 5 on bottom. Okay, so this will be 5 over 2. So 5 halves, or if you want 2.5. So that's the slope, right? If we were to go back and say, well, no, what we really want is to call this point 1 and this point 2. Well, what happens? Okay, so we'll do m equals, sorry, trying to make this neat, y2 minus y1 over x2 minus x1, because that's the formula. But now that we've swapped the order of what we labeled the points as, this is y2 and this is y1, so 4 minus 9 on top. And then on bottom, this is x2, and this is x1. So 5 minus 7 on bottom. Okay, so what we're going to get is on top, -5, and on bottom, -2. But a negative divided by a negative is a positive. These negatives cancel out, and I just get 5/2, which is the same thing. Okay, so when you take this fraction, the rise over run, if you swap the order of the top and the bottom, both, you get the same answer. So it doesn't matter which point you call point 1 and point 2. Just label them and go from there. It doesn't matter which choice you make for that. So either of these is fine. So we still need to find the equation of the line. So I'm going to be using this formula here, the point slope form. But I'm running out of vertical room, so I'm going to do it over here. Okay. So y equals m times x minus x1 plus y1. Okay. So m is 5/2 times x minus, well, x1 is 7, right? If I want, I can use this one instead. It'll work. It doesn't matter which one I pick, but currently that's the one that's labeled 0.1. So x1 is 7 plus y1, which is 9. And then I can distribute this. So this is 5/2 minus 35/2, because 7 times 5 is 35. Plus, I'm going to go ahead and get a, well, let's do this in steps. I don't want to do too much all at once. Maybe this is already, kind of challenging to keep up with. So the 9, I'm going to think about, well, I want to ultimately combine these, and I don't want to use a calculator unless I really need to. So I'm going to rewrite this 9 as 9/1. Okay, so now I need a common denominator so that these two can combine. So I need to multiply top and bottom of this by 2. So that I get the right denominator, right? So I'll have 5. Oh, I forgot to put an x. Right, this x, oh, sorry, wrong tool. This x I forgot to put right here. So 5/2 x is what I should have. So put that in there. Okay, so 5/2 x, and then of minus 35/2 plus 18/2. So -35 plus 18 is -17. So I get 5/2 x minus 17/2. That's the whole thing. Okay, so that's the line. All right, well, let's go to this other one. And we won't do this all the different possible ways. We'll just go with, we'll call this point 1, call this point 2. So m equals y2 minus y1 over x2 minus x1. Okay, so this will be -7 minus 2 over 4 minus -3. And sometimes you're going to have a double negative, so you have to be careful with your pluses and your minuses. Because if you get one in the wrong place, well, then obviously you're going to get the wrong result. So on the top, we have -9. And on the bottom, we have 7. Because 4 minus -3 is really 4 plus 3, so we get 7. So -9/7. Okay. Then I can go to that formula and do y equals m times x minus x1 plus y1. Okay. So my slope is -9/7 times x minus -3 plus 2. Okay. And we're kind of running out of room here. So let's put that over here. Okay, so let's do one simplification at a time. When you subtract a negative, you're really adding. So this is y equals -9/7 times x plus 3 plus 2. Then I can distribute the -9/7 and probably also write it a little bit neater. So this is -9/7 x minus 9 times 3 is 27/7 plus 2/1, because I want to get a common denominator. So I need to multiply 7 on top and bottom here. So I get y equals negative 9 over 7x minus 27 over 7 plus 14 over 7. So I get y equals negative 9 over 7x minus 13 over 7. And there's my line. Okay. All right. And we're almost done here. Let's go on to the next one. So solve each equation for y in terms of x. Write your answers in slope-intercept form. So slope-intercept form, that means this form right here. Y equals mx plus b is the format that we need. Okay, so no parentheses. You might have fractions, but you can't leave parentheses. So what we're going to do is, I'm going to use. Oh, I'm sorry. I was thinking of the wrong one. No, never mind. We don't need to use this one. Sorry. Basically, we just need to take this equation and get y by itself and make sure to not have parentheses so that it looks like this version. It needs to look like this version, no parentheses. That's what it means by, say, write your answers in slope-intercept form. Don't have parentheses is essentially what that means. Okay, so it just means get y by itself. Isolate y on the left. You want y equals the rest of whatever you have. So I'm going to subtract 7x on both sides. And on the right, it can't combine with anything. So I'll just have negative 7x plus 25. So negative 5y equals negative 7x plus 25. And then I'll divide by negative 5 on both sides. Okay. So this will be y equals, when you have an expression like negative 7x plus 25, you have multiple pieces in the numerator, and you're dividing by a number, you can rewrite that by dividing into each number individually. So you can do like, or each term individually, I mean to say, not each number. So this is negative 7x over negative 5 plus 25 over negative 5. And then you just reduce from there as much as possible. So y equals, the negatives will cancel in this first one. Negative 7 over negative 5 makes positive 7 over 5. And the x I need to write after the fraction. Whenever you have something like 2x over 3, that's the same as 2/3 x. And one way to think about why that is it's kind of like having 2 over 3 times x over 1. Hopefully it's clear that the 2 and the x go together in the numerator. But then you don't have to have the over 1, so you just write this as 2/3 times x, no fraction needed. So these are two different ways to write the same thing. And there would otherwise be nothing wrong with writing this as 7x over 5, except problem said use the slope-intercept form, and the slope-intercept form has to have like this, where you've got a number times x. It's the y equals mx plus b format. So the x has to be next to the fraction, not on top of it. That's just the way the format works. Okay, and then 25 minus negative 5 is negative 5. So there we go. There's the slope-intercept form of that one. So that just basically just means get y by itself is essentially it. Moving on to the next one. So similar thing, I just need to simplify this. Now what I can do is I can start by, well, there's a couple of things. Let's do this. Let's divide by 2 on both sides. So let me rewrite this. So I have negative fraction x minus 3 over 5 equals 2y. So there's several things here. I need to move the 2 eventually because I want y by itself. Also, that fraction, I need to separate into 2 fractions because x can't be inside the fraction. It has to be next to it, so I need to break this up. And also that minus out in front can be applied to the numerator. So what I'm going to do first is rewrite this like negative x minus 3 over 5. It's the first thing. Remember, when you have a negative on a fraction, it can go in front, it can go on bottom, or it can go on top. It's up to you. I'm putting it on top right now. I'm going to distribute this this negative on across the parentheses. So I'll have negative x minus negative 3, or in other words, negative x plus 3 over 5 equals 2y. And from here, I'm trying to decide what do I want to do next, because I have options. Oh, did we skip one? No, okay. Because I have options as to what I do next. What I think might be best is I'm going to divide by 2 on both sides. Or in other words, multiply by 1/2 on both sides. Multiply by 1/2. It's probably the best way to proceed. So on the left, I'll multiply the two numerators together. So 1 times that negative x plus 3 will just be negative x plus 3. And then 2 times 5 makes 10. So on the left, I'll have negative x plus 3 over 10 equals y. Okay, so I'm almost done because y is by itself. I'm going to rewrite this with y on the left. I'm just swapping the order, left versus right. You can always do that in an equation. Just switch the order. And then I'm going to break up this right-hand side to have two fractions. Instead of negative x plus 3 all over 10, I'll have negative x over 10 plus 3 over 10. Okay, I'm still not quite done because this is not quite in the mx plus b format. This x on top here needs to move out of the fraction, needs to move next to it, as we talked about a minute ago. So this is negative 1 over 10 times x plus 3 over 10. So that is the slope-intercept form for that one. Okay. And again, there's more than one way to do this. The order in which you apply these steps, basically to get y by itself, there's sort of only one overall way to do it. You get y by itself. Yeah, but how? Like in what order do you move things around? That's up to you. So there's more than one perfectly good way to do this. Yeah, so let's keep moving. We're almost done here. Well, with the graphing part, and then we have these inequalities. So we're almost done here. This one says find and plot the x and y intercepts and graph each line. Okay, so x and y intercepts, what does that mean? Whenever you have a graph, the x and y intercepts refer to the points on the graph that touch the x and y axes. So I'm just gonna make like a random graph real quick just to talk about what that means. So if I make a graph like this, okay, which is not the graph that we have, if I just make it up for a second, then the places where this graph touches the x-axis, those x-coordinate numbers, those are called the x-intercepts, okay? And then the place where the graph touches the y-axis, that number, in this case -1, that's the y-intercept. So the graph of a function will generally have one y-intercept and one or more x-intercepts. Some equations or some functions won't have an x-intercept, or they won't have a y-intercept. That happens sometimes. But wherever the graph touches the axes, that's where that's occurring. The thing to note about that is this: if you're looking at this point right here, where the graph is touching the x-axis, this will be some x value. Hold on, make this more readable. This will be some x value, and the y-coordinate will be 0, because if you're on the x-axis, the y-coordinate is 0. Remember that the y-coordinate, it's a measurement of vertically where are you. Are you, like, if y is positive, then you're above the x-axis. If y is negative, you're below the x-axis. So if you're on the x-axis, then y is 0, because you're not up or down, you're on the horizontal line. Okay. Similarly, if you look at the y-intercept here, this is always going to be 0 in the x-coordinate, and the y-coordinate is whatever it may be. Just depends, okay? So when we want to look for the x and y intercepts for an equation, all we got to do is, if I want the x-intercepts, is I start by saying, well, I know y is 0, so I'll plug in 0 for y, solve the equation, and I get a number for x. That's my x-intercept. Okay. If I want the y-intercept, well, I know that at the y-intercept, x is 0, so I plug in 0 for x, solve for y, get a number. That's the y-intercept. Okay. Yeah, so let's do that. So that's just conceptually what we're doing, but I wanted to explain it before just doing it without any reasoning. So fiddling with the interface here. Okay. So for the x-intercepts, I want to plug in 0 for x. Sorry, 0 for y. Sorry. So 4x minus 3 times 0 equals 12. So 4x equals 12. Divide by 4 on both sides. X equals 3. So 3 is the x-coordinate of the point where the graph touches the x-axis. So that means that 3, 0, like right here, that is the x-intercept, okay? And I know that the quality on this graph is kind of blurry. That's what we have. We'll just work with what we have. If you're zoomed out, it looks fine. When you're zoomed way in, though, it looks kind of blurry and not the best. Maybe at some point I'll remake all of these with somewhat nicer diagrams that aren't so blurry. Anyway, now to find the y-intercepts, well, plug in 0 for x and solve the equation. So 4 times 0 minus 3y equals 12. So negative 3y equals 12. I'll divide negative 3 on both sides, and I get y equals, well, 12 over negative 3, right? But that's negative 4. Oops. That's negative 4, okay? So negative 4, right here, y equals negative 4, that's my y-intercept. Now, if I connect these with a line, I'll be graphing that line. So there's just really quick, have a line. I'm going to extend it, though, because really a line, it extends past just those intercepts. So I just want it to be like filling the entire grid with the straight line. So that's what it looks like to find the x and y intercepts and then graph the line. If you have the intercepts, just make a straight line connecting them and then extend it past those intersection points. And there's your graph of a line. Okay. Okay, let's go ahead and do this one. Okay, so same thing. If I want the x-intercept, hold on, sorry, struggling with the interface here. Okay, so if I want the x-intercept, or intercept plural potentially, right, I need to plug in 0 for y. So x plus 2 times 0 equals 8. This means that x equals 8. So that was easy, right? So 8 is my x-intercept. So that's about here-ish, okay? And then if I want the y-intercept, I put in 0 for x. So 0 plus 2y equals 8. So 2y equals 8, and I can divide 2 on both sides. Y equals 4. Okay, and then I can connect those two with a line that I'll extend past those intercept points, just so it doesn't look like it's a line segment that only goes between them, but it's actually a straight line that covers the whole grid. Anyway, that's how you do that. Okay. Moving on. Yeah. Solve each inequality. Write your final answers in interval notation. So, yeah, so there's also a lot that's under the hood here. I will just show how to work the problems. Again, if you need help understanding the whys of some of this, email me. We'll get on a Zoom call. I'll be more than happy to explain it. It's just in the recording, I don't know what people don't understand until they tell me, with some exceptions. Obviously, there's some things that I know people have trouble with. For this one, I'll just show how to do it. Okay, so when you are solving an inequality, it basically works very much like an equation with some exceptions. So let's go down here. So whenever you have an equation, you can basically do anything to both sides. Right? You can add on both sides. Wow, sorry. So you can add on both sides, subtract on both sides, multiply, divide, so forth. When you have an inequality, so like a less than, a greater than, a less than or equal to, or greater than or equal to, it's mostly the same, but there's some caveats. So if you add or subtract on both sides, that works just like as with an equation. If you multiply or divide, it's more complicated. Okay. If you multiply, sorry, apparently I can't think today. If you multiply or divide by a positive number, then it just works normally. But if you multiply or divide by a negative, then it's different. So if the number is positive, then you just do it like you would with an equation. No difference. If the number you're multiplying or dividing is negative, then you have to flip the sign. If you just think more complicated, like squaring both sides, square rooting both sides, stuff like that, then it gets complicated. So we're not going to deal with that. I think in this class, we don't need to deal with that at all. If this were the STEM algebra class, then we would. But in this class, we don't really need to, so we skip that. So if you're interested to see what that would be like, again, email me. We'll get on a Zoom call. I'd be happy to explain it. It's just we don't need that for this class. So what we do need to know is basically you can add, subtract, multiply, divide both sides, but if you multiply or divide by a negative, the sign flips direction, okay? So up here, I'm going to add 7 on both sides. So I get 4x is less than or equal to 16. I'll divide by 4 on both sides. So x is less than or equal to 4. No negatives were involved, so I don't flip the sign. And then that's the inequality solved. So the solution would be all numbers less than or equal to 4. So like 4, 3, 2, 1, 0, -1, so forth. But also decimals like 3.7 would be a solution because 3.7 is less than or equal to 4. It says, though, that we're going to write our final answers in interval notation. Okay, interval notation. And maybe you're already familiar with that, but just in case, here's a reminder. So basically the way the interval notation works is this. I think it's easiest to explain if we have a number line. So if I wanted to graph this list of numbers or set of numbers, what I could do is make a number line, mark 4, because that's the number that's relevant to, that's the boundary between solutions and non-solutions. Numbers like 5 are not solutions, right? Those are not less than or equal to 4, so we don't use them. Numbers like 3, these are less than or equal to 4, so we want to include them. So one way to do this is to like shade in the left-hand side, including numbers that are less than 4 to say, oh, we're including numbers that are less than 4. And then at 4, we can put in a circle that's filled in, and that is because there's a less than or equal to, so 4 is actually one of the numbers to use. If this were different and this was strictly less than, x is less than 4, then we'd put an open circle to indicate 4 is not included. But it is included, so we'll just do this. Okay, so that's one way of indicating the solution is through a number line. You can do that. What I want you to think about is how on a number line, you were listing all the real numbers, all the whole numbers are there, the fractions and decimals are there sort of implicitly, like 2/3 is there, I just haven't labeled it, right? 1.7 is there, I just haven't labeled it. What I want you to think about is this. If you think about all the way at the left end of the number line, like negative infinity is all the way at the left, and then on the right, positive infinity is all the way at the right. So if I'm saying that we're including everything that's less than 4, as well as 4, then that means that my interval is, actually, let's do it this way. My interval is starting over here at negative infinity, and it's going up to 4 and stopping at 4. Okay, so to write that interval notation, I'm going to say that I'm starting at negative infinity, which is another way of saying include all the numbers to the left. It's like you're starting at negative infinity and coming towards 4 from the left of it, and including all the numbers you pass over. Negative infinity is not a number, it's more of a concept. It's the left edge of the number line, but we use that notation to indicate we're including everything from the left, okay? Up to 4, and then I'll use a bracket to indicate we are including the 4. If the problem were different, and this right here, like this was strictly less than, and this was an open circle instead of filled in, we would do a curved parenthesis. That means don't include 4 as part of the interval, okay? But that's not the situation. We are including 4, and that's because of the fact that x is less than or equal to 4, and 4 qualifies because 4 is less than or equal to 4. That's what the or equal part means. Anyway, so hopefully that kind of made sense. I'm not going to draw the number line out for all of these, but it's basically, once you get to this point, if you're familiar with what to do, you can figure out the interval without drawing anything. But if you're not so familiar, you might need to draw this out to see where your interval starts and stops. Okay, let's go to the next one. So this one, this is a strict inequality. The left-hand side is greater than the right-hand side. I'm going to start shuffling symbols around, and there are options. Whether you isolate x on the left or on the right is up to you. I'm going to stick to isolating x on the left, although it's not necessary. If I want, I can move that one over here. Instead, I'm going to move this one over here. Okay, so I'm going to subtract x on both sides. And I'm going to write my steps out so that this is a little bit clearer, because this one's a little bit more complicated. So negative 3x plus 3 is greater than negative 5. I'll subtract 3 on both sides. Remember, when you're adding or subtracting, it's just like with an equation. You don't change the sign. The inequality symbol doesn't change when you're adding or subtracting, okay? Now, I have a negative number in front of x. I need to divide by negative 3 on both sides, okay? Now, when I do this, in the next line, my inequality changes direction. Because I've divided by a negative, that changes the direction. I'm going to skip talking about why. Again, ask me, Zoom call. You know the drill by now. You've heard me say it enough. So we're going to get x is less than 8/3. A negative divided by a negative is a positive, so we get 8/3. So then the interval, since x is less than 8/3, I can think about my number line. I don't necessarily want to draw it out every time, but I can think, okay, 8/3 is the position that splits solutions from non-solutions. This is a strict inequality, so 8/3 is not part of our answer. So I'm going to put an open circle, meaning don't include 8/3. And since I'm taking things that are less than 8/3, that means I want everything to the left. Basically, when you have x less than, your interval starts at negative infinity. It's pretty much how it's going to go. So this will be negative infinity up to 8/3, not inclusive. I'm using a parenthesis, not a bracket, because this is a strict inequality, and we are not including 8/3 as part of our solution. So this is a curved parenthesis because we're not including 8/3. Okay. Okay, we're almost done, I think. Yeah, we got one more. So, much like with the earlier equations in which we had fractions, I like to clear fractions first. To me, that's just the easiest thing to do. So I'm going to rewrite this. X plus 3 over 8 minus x plus 5 over 5 is greater than or equal to 3/10. Okay, and I'm going to look at all my denominators, and I'm going to figure out, well, what's the least common multiple? And you might be able to tell just by looking at it. 40 is a multiple of 8 and a 5 and of 10, and it's the smallest number that does that. It's like 20 is not a multiple of 8, although it is a multiple of 5 and of 10. 30 is a multiple of 5 and of 10, but not of 8, right? 16 is a multiple of 8, but not of 5 or 10. So 40 is the smallest one. Sometimes especially if your numbers are small, it's not too hard to see what that is. Other times it's more challenging. Again, if you need help figuring that out, like how do I decide what the least common multiple is, we can talk about that in a Zoom call. Anyway, so I'm going to multiply 40 on both sides. And I'm going to do something a little bit different on, on the right-hand side. What I'm going to do is, let's do it this way. Let me back up. Let me backtrack. Let's say we're going to multiply both sides by 40 over 1, just so it's a little bit more on the nose that we're utilizing properties of fractions, okay? Now on the right, the 40 and the 10 will reduce, right? So this will be divide by 10, you get 4. Divide by 10, you get 1, okay? So we'll have 12 on the right-hand side. On the left, I'm going to do something a little bit different. What I'm going to do is I'm going to think about, okay, I'm going to multiply 40. Oh, sorry, wrong tool. I'm going to multiply 40 on to the numerator of both of these fractions. Now, what I'm going to do is before I write it down, I'm going to think, okay, 40 will multiply against the numerator of x plus 3 over 8. Well, 40 and 8 reduce. Kind of like over here, 40 and 10 reduce. So here's what I'm going to do. I'm going to write this as 40 over 1 times x plus 3 over 1. I think that this will be a better way to explain what I mean. I'll show you the written step and point out what you don't have to write if you want to cut corners a little bit. Like if you're confident that what you're doing is right, you can cut corners a little bit. Okay, so greater than or equal to 12, right? So what I'm going to do is here, I'm just going to reduce the 40 and the 8 by doing 40 divided by 8 makes 5. Or in other words, 40, cancel out a copy of 8 from it. You have a 5 left. 8, cancel out the 8. And then over here, I'm going to say, well, that 8 and that, or sorry, not the 8. The 40 and the 5 cancel as 8 and as 1. Divide 5 into both of those, and you get 8 and 1. And then my denominators are all handled, right? My denominators are all 1s. The denominators went away in one step. So then I'll have 5 times x plus 3 minus 8 times x plus 5 greater than or equal to 12. This step I could have skipped writing if I wanted to. Like I can write this part out. Sorry, write this part out. Write this part out. And then instead of writing this out, I can just think, oh, well, the 40 and the 8 will reduce to make 5. Just write the 5 down and put the x plus 3 with it. Or the 40 and the 5 will reduce to make 8. We'll just put the 8 down and then write the x plus 5 next to it. So you have options. You have opportunities to cut corners a little bit. If you feel confident in what you're doing, you can cut corners. You don't have to. It's not necessary. Just you might want to sometimes. Anyway, so now I can distribute this 5 here and this 8 here. We got to watch out, though. So this 5 will multiply against the x to make 5x and against the 3 to make 15. Okay. Now, what you have to be careful about is thinking about, oh, well, this 8 makes 8x and 40. Not quite. We have to be careful. This minus goes with the 8. So it makes negative 8x and negative 40. Okay. So this will be 5x plus 15 minus 8x minus 40. A lot of people forget that minus because they don't associate the minus with the 5, but the minus goes with the 8 wherever it goes. So when that 8 turns the 5 into a 40, the minus goes with it. Okay. And of course, that's greater than or equal to 12. And on the left, I can combine like terms. So I get negative 3x because 5x minus 8x minus 25 because 15 minus 40. I can add 25 on both sides. And then divide by negative 3 on both sides. And when I do that, when I divide by a negative, was that one also 3? It was also 3. Huh. So that's a coincidence. Anyway, so when I do that, the inequality changes direction. So you have to be sure not to forget to do that. So this will be x is less than or equal to, sorry, I hesitated for a second because I thought maybe I made a mistake. Negative 37 over 3. And again, this could be, if you want, negative 37 over 3 with the negative in front, or 37 over negative 3. Where you put the minus sign is kind of up to you. So again, I have I'm going to do this without the number line this time. I have x is less than or equal to. That means I'm starting at negative infinity. Okay, if you have x is less than or equal to, you're starting at negative infinity. Then we're going up to negative 37 thirds. And because this is less than or equal to, that means that number is part of my solution because negative 37 over 3, that is less than or equal to negative 37 over 3. Anyway, so yeah, that was about 90 minutes. I think in the future, some of these will be shorter, but this one just covered so many different things that it took a while. Yeah, so I'm going to, I had that technical hiccup somewhere towards the beginning, so actually I have two files recorded. I have to go and merge those together, and then this will be on, I mean, obviously if you're hearing this, it's on YouTube already. So yeah, in the future, I'll try to, keep these not super, super long, keep them somewhat brief, as much as possible. I'll try to avoid going off on tangents, explaining stuff that maybe you don't need, and I'll try to reserve that for people to ask questions. But yeah, that's basically the Module 1 stuff. You can use this. Be sure to fill out the PDF that's given in Canvas, and basically like rework all these problems. And if you want, you just straight up copy what I did. If that works better for you, you can just copy what I did, like by hand, right? And then turn that in as a PDF, and then the TA will mark that you did it. Yeah. So if you have any questions about any of this, please don't hesitate to email me. And yeah, I look forward to hearing from those who need help so I can help.